Let's take a look at the idea of one-sided limits. Let's start with definition. A right-hand limit. Suppose f is defined for all x near c with x greater than c. If f of x is arbitrarily close to L for all x greater than c, yet sufficiently close to c, then we say that the limit, we use that LIM notation that we did before, as x approaches c, and this time I'm going to put a little positive as a superscript. So this is telling me I'm coming from the right, of f of x is equal to L. Okay, let's see what this means with the graph. So again, these definitions are kind of nice, but there are times when the words just feel like a big jumbled mess, and we need to see a picture to see what's going on. So here's c, and here's x, and as I approach x from the right, what this is saying is right here is L. So as x approaches c from the right, f of x, which is this curve obviously, gets infinitely close to L. Now the left-hand limit is exactly the same thing, only coming from the other side. Suppose f is defined for all x near c with x less than c. If f of x is arbitrarily close to L for all x less than c, yet sufficiently close to c, then we say the limit as x approaches c. This time I'm going to, c. This time I don't want you to get confused. That's not, that little spot shouldn't have been there. Okay, so c. And this time I'm going to use a superscript of a negative. That tells me I'm coming from the left, of f of x is equal to L. So I will draw this same picture, or at least similar as I can here. I have this value of c that I'm approaching, and this is L. So as x gets infinitely close to c, sufficiently close to c, what's happening to my graph? My graph is approaching L. So that means the limit is L. So limit from the right in this case is L, and the limit from the left in this case is L. In this case, both L's are the same because I get, in a way, in theory anyways, this is the same function. I'm approaching the same value of c here. So let's consider a maple-generated graph of f of x equals x squared minus 4 over x minus 2. We've looked at this before. There it is. It's just a line. But what we're not seeing is the hole that's here. That's what we're not actually seeing in this case. So why can't we see this hole? Well, I may mention it earlier that this hole is infinitely small, and I don't know how Maple would make an infinitely small hole that you can see. But let's go ahead and consider the limits. Let's do this graphically. I know that this function looks like this, and for x equals 2, that's that hole that we talked about before. So, therefore, I can say the limit as x approaches 2 from the left of f of x equals 4. As x gets infinitely close to 2, oops, I don't want green, I want red. Infinitely close to 2, this function gets infinitely close to 4. We can also look at this and see that the limit as x approaches 2 from the right of f of x, well, as I get infinitely close to 2 from the right, what's happening to my function? Again, it's getting infinitely close to 4. So this limit is also equal to 4. Now, this brings us to yet another definition of sorts. If the limit as x approaches c from the negative, and I'll write this again to make sure you can see that as x approaches c from the left, of f of x, if that's equal to the limit as x approaches c from the positive, in case that's a little bit small in the video, of f of x, if these both equal L, okay, and L is in R, this means a real number, then what this is saying then is that the limit as x approaches c of f of x is equal to L. I kind of alluded to the fact earlier that when we write it in this form as x approaches c, the implication there is that we're looking at the left and the right. So if the left-hand limit, this is a left-hand limit, if that equals the right-hand limit, then we say the limit exists. So if the left-hand limit is equal to the right-hand limit, then we say that the limit exists and it's equal to this value L, whatever it is that we approach from the left and the right. So therefore, we can say that the limit as x approaches 2 of x squared minus 4 over x minus 2 is in fact equal to 4. That's what we just saw in the graph. Now again, that is not saying that f of x, if this is what we're thinking of here as f of x, that is not saying that f of x equals 4. It's saying the limit as x approaches 2 of f of x is 4. That's two different things. So the limit is 4, even though at 2, in this particular case, f of 2 does not exist. So let's take a look at a couple of graphical examples here. So the first one, I have a function that looks like this. This is my f of x. And let's just say this is at 2. So this is x, this is y. The limit, I'm going to pick another color here. This is the horizontal line. Oh, that's a bad color. There we go. This is the horizontal line at 3. So this is y equals 3. So in other words, there's 3 right there on the y-axis. So what is the limit as x approaches 2 of f of x? Well, as x gets infinitely close to 2 from both directions, on the graph I'm approaching 3. This line y equals 3. So this limit is equal to 3. So take another function, another graph. Let's just say it looks, let's see, here's 2, 4. And let's take a look at, see, let's just say this is x equals 3. Have a function that looks like this. And now I want to know the limit as x approaches 3 of f of x. What is that? Well, to deal with that, I'm going to need to take a look at the left-hand limit and the right-hand limit. So the limit as x approaches 3 from the left of f of x, that looks like it's 4. The limit, sorry, I'm kind of running out of room here. The limit as x approaches 3 from the right of f of x, well, that's here. That looks like that limit is going to be 2. The left-hand limit does not equal the right-hand limit. Therefore, the limit does not exist. The left-hand limit does. Right there's the left-hand limit. The left-hand limit looks like it's 4. The right-hand limit, right there's the right-hand limit, that's 2. These are not equal to each other, so we say the limit does not exist.